Now earlier I said that this new property, entropy, was going to allow us to examine the efficiency of individual processes. So that's what we want to turn our attention to now, is the efficiency from a second law perspective of several different components that we've been studying in the class. So the first thing we want to look at is the isentropic efficiency of a turbine. So this is a new term, isentropic efficiency, which we'll be defining here in a moment. So we have a turbine with certain inlet and exit conditions. And what the first law has already told us about this turbine is that the work that it produces on a per unit mass basis is H1 minus H2. Now, in getting to that simplified version of the energy equation, remember that we said that this turbine was adiabatic, so no significant heat transfer with the surroundings, and we're going to continue to say that here. Well, if we apply the second law to this same control volume, so we have a control volume around this turbine, then we want to see what it tells us about this situation. Well, first of all, it's a steady state situation. We had to assume steady state to get to this. So ds dt is going to be 0 because it's steady. Remember, Q is 0 in the energy equation, so Q will also be 0 in the entropy balance. And we have a single inlet and a single exit, so these summation signs disappear, and of course the mass flow rate is the same in both. So we could rewrite this. 0 equals common mass flow rate, S1 minus S2 plus the irreversibilities. So this tells us that if we have a perfectly reversible turbine, that means this would be 0, so S1 would have to be equal to S2. So the entropy at the inlet and the exit would be the same if it were a perfect turbine. However, in general, there's going to be some irreversibilities in there, and so the entropy at the exit is going to have to be bigger than it was at the inlet, because this now is not 0. Well, this brings us to the definition of the isentropic efficiency of a turbine. So the isentropic efficiency of a turbine is defined as the work that it produces divided by the work it would have produced if it were isentropic. So there's some new notation here. Notice this extra subscript S on the turbine work. That extra subscript S is going to show up quite a bit in the next little while, and it always means the same thing. It means this is what that value, and in this case the value is the turbine work, this is what that value would have been if the process were isentropic. So it's not the real turbine work, it's the ideal turbine work. So remember, the numerator here is the actual work produced by this turbine, so that's some value. And this is what it would have produced if it were isentropic. Now that's what it would have produced operating between the same two pressures and with the same inlet conditions. So you can imagine two turbines sitting side by side. Their inlet conditions are exactly the same. Their exit pressure is exactly the same. One is a real turbine producing this amount of work, and one is a hypothetical or an ideal turbine, and it would produce this amount of work. Well, notice that the denominator here is always going to be bigger than the numerator, because an isentropic turbine will always produce more work than a real turbine when operating with the same inlet conditions and the same exit pressure. So this isentropic efficiency is always less than 1. If we happen to be looking at an isentropic turbine, then of course this efficiency would be equal to 1, because these two things would be the same. Now what we can do is represent each of these works by a change in enthalpy by using this equation. So that tells us that the isentropic efficiency of a turbine is H1 minus H2, so that's the real work, divided by H1 minus H2S. So notice this tells us again we're looking at the same inlet conditions. These H's are exactly the same. We're feeding these two turbines exactly the same substance. And the extra subscript here is on the exit enthalpy. So this H2S is what the enthalpy would have been coming out of this thing if it were isentropic. So the H2S corresponds to the WTS. Those are both the isentropic turbine. Now we want to take a look at this on an HS diagram. So this is a new set of coordinates, but it's very similar to a TS diagram that we talked about earlier. So this is called a molar diagram. So our coordinates are enthalpy on the vertical axis and entropy on the horizontal axis. So we have our inlet conditions for the turbine plotted here. So we're at some high pressure and some value of H up here, H1. And we go through the turbine down to some lower pressure, P2. So this is where using entropy as a coordinate on one of our property diagrams becomes so useful, because we're going to be able to see at a glance whether this process is isentropic or not. So if we first of all look at the isentropic case, so if this is a perfect 100% efficient turbine, then that means the entropy will not change as we go through that turbine. So we will drop from point 1 straight down to point 2. And because we're looking at the isentropic case, we have this extra subscript on point 2. So we call that point 2s. And its main characteristic is it's directly underneath point 1, because we got from 1 to 2s through an isentropic process. So no change in entropy, vertical line. Now the actual turbine is going to have an increase in entropy, and how dramatically that increases is a measure of how strong the irreversibilities are. But if we just show this schematically on our HS diagram, we'll see the real turbine drifts off to the right as it drops from point 1 down to P2. It still ends at the same pressure, so point 2 and point 2s are on the same line of constant pressure, but because it drifted to the right, it hits P2 at a higher value of H. So notice this value of H down here will be H2S, and this value of H up here will be H2, because those go straight across to those 2 points. So the real turbine does not produce as much work as the isentropic turbine. This is H1 up here, and so the distance from there to there, the change in enthalpy from there to there, is the real work, WT, and the larger work, the change in enthalpy from here down to here, is WTS, the isentropic work. So we can see at a glance from this that the real work is less than the isentropic work. Next, we want to look at the isentropic efficiency of a compressor. And remember, when we did this for the energy equation, compressor is just the opposite of a turbine. Very similar thing is happening in the two of them, just in an opposite direction. So because of that, our definition of the isentropic efficiency for a compressor is the inverse of what it was for a turbine. Notice the ideal work is now in the numerator, and the real work is in the denominator. That's because now the isentropic work will be smaller. Because if you have a perfect compressor with no irreversibilities, it is going to take less work to compress a substance between 2 fixed pressures than it would take if there were some irreversibilities. So in terms of enthalpy changes, again, this becomes H1 minus H2S, because we're looking at the isentropic work, and this becomes H1 minus H2. And again, common inlet conditions to these two compressors, the real one and the isentropic one, so that H is common. The inlet enthalpy is the same. It's the exit enthalpy which is different. And if we look at this on our HS diagram, again, we're now compressing, so we're going from a low pressure up to a high pressure. The isentropic compressor would go straight up, so point 2s would be directly above point 1. The real compressor is going to drift to the right as it goes up, because irreversibilities are causing entropy to increase. So the real compressor would follow a path like this, and it would end up at a value of the enthalpy that is larger than if it had been isentropic. So H1 minus H2 is always going to be bigger than H1 minus H2S because it has to go up farther to get to this final discharge pressure, P2. The last component that we'll look at is the isentropic efficiency of a nozzle. And this is just defined as the actual kinetic energy at the exit, V squared over 2, and the subscript E reminds us it's the exit, divided by what that kinetic energy would have been if it were isentropic, so no friction or sudden expansion or anything in the nozzle. And that kinetic energy is always going to be larger. So the isentropic efficiency of a nozzle is the real case over the ideal case, and that'll always be less than 1. And how close to 1 it is a measure of how close to isentropic that process is. And just as we saw for the turbine and for the compressor, we can express these kinetic energies as a function of enthalpy changes. So again, the same inlet conditions and the same exit pressure, but the enthalpy at the exit is different between the real case and the isentropic case.